звук. Меня слышно? Так. Ну, вроде сейчас должно быть все как обычно. То есть. So today we're going to start new chapter, which is a relatively short chapter about associated primes. So I think this is chapter 6. Associated primes. And primary decompositions. And the first section will be associated primes. So, of course, I'll start with the definition. So, in the definition, I assume that I fix a module. So, M is an R module. Then we already know that we can associate a set of prime ideals to this module. So, this is the set of which we called the support of a module. Now we're going to associate another set of prime ideals, which is usually a little bit smaller set. So, in the reasonable case, this is a finite set. So, the definition is the following. So P in the spec of R is called associated with the module M if there is an element, say X, in the module which is a non-zero element such that the annihilator of this element is precisely this prime ideal P. So this is definition, and intuition, well, is kind of one of the basic definitions in commutative algebra, but you might try to think about this as generalization of the eigenvalues. So for example, so we can consider the following example. We take a ring to be just a ring of polynomials in one variable, the module, well, just finite dimensional vector space. So dimension, or maybe just use notation V. So dimension of V over K is finite. Well, then this X, which is a non-zero element, will be, so in P is just, let's, for simplicity, let's take K to be algebraically closed and take a maximal ideal. So here we have zero ideal, which is a prime ideal. All other prime ideals are maximal ideals. So take T minus lambda. So then this P is equal to the annihilator of some vector means precisely that this vector is an eigenvector and lambda is an eigenvalue. Of course, this is not a kind of a very good explanation that this is n-log of eigenvalues, well, because in this case you can also as well study support, and the support will be exactly the same set of prime ideals. So this is not a complete analogy, but at least this gives us some intuition. So we saw many times in commutative algebra that it's quite reasonable if you have something for maximal ideals, try to understand this for prime ideals. So this is what we're doing here. So we're just trying to formulate a condition that X is kind of an eigenvector, but for the prime ideal. So this is a reasonable condition. Okay. Now, by the way, I can use this space for a little remark, which might be important, actually for two remarks. So first remark, if you have this, if P is, by the way, notation for this is just S of n. So this is the set of all associated primes. And if ring is not clear, we can use the subscript R. So first of all, and the first notation is that P belongs to associated primes of the module M if and only if we have a submodule R module P inside this M, which is exactly just a cyclic submodule generated by the X. And since the annihilator of the X is P, well, this is exactly this quotient. So this is the first remark. And the second remark, well, so a little exercise. If you want to understand associated primes of the quotient, well, I claim that this is a set that consists of only one element. Okay, now let's prove first proposition. Proposition. So let P be a maximal element of the following set. So you take annihilators, so these are some ideals. So annihilators of elements X such that X is any non-zero element in the given module. So then P is associated with the module M or to the module M. So in particular, so we know that the maximal element is an associated prime, but we don't know in general that for a given set of ideals there is a maximal element in this set. But we know this definitely when the ring is Noetherian. So in particular, if R is Noetherian, then in this set we have maximal elements. So we can conclude that for any M which is not equal to 0, the set of associated primes is not empty. Okay, proof. So the only thing I need to show in this statement is that I take this maximal element in this set and I need to show this is actually a prime ideal, right? So if I can do this, that's the end of the proof. Well, let's take a couple of elements. So elements, say B and C in the ring R, such that the product BC is in the prime ideal P, which annihilates some element X. So assume that C is not in this prime ideal. So then I want to show that actually B in this, well, I do not know yet that this is a prime ideal, so assume that C is not in P. I want to show that B is necessarily in P, and then I can conclude that P is a prime ideal. Okay, so C is not in the ideal P. This means that Cx is not 0, right? So C doesn't annihilate element X. Cx is not 0, but P belongs to the annihilator of the element Cx, right? If I take any element in the P, it annihilates X, so it definitely annihilates the product. Well, the ring is commutative, I can just move around this and conclude that, so P is a subideal in the annihilator of Cx. But then this immediately tells us that P is actually annihilator of this element Cx. Well, since we assume that P is a maximal element in such set of ideals which are annihilators of some elements. So, and then what we can see? Well, we can see that B is an element in P, right? So we already know that the product BC is in P, meaning that this annihilates X, so B annihilates Cx, right? But this means exactly what I want to show, right? I started with product that belongs to an ideal. I assume that one element is not in the ideal, and the other element is in the ideal. Okay, so corollary. So we can generalize this slightly. So I would say that the quite reasonable theory can be developed over an Noetherian ring. So usually when people discuss associated primes, they assume that the ring is Noetherian. So in some textbooks you can find even that there's a chapter on Noetherian rings and there's a section about associated primes. So it can be generalized slightly for Noetherian modules. So the following corollary tells us the following, that if M is a non-zero Noetherian module, so then the set of associated primes is again not empty. So the main conclusion here that in some cases you can say that the module is non-zero if and only if the set of associated primes is not an empty set. So we want to consider the case of a Noetherian module, but not necessarily a Noetherian ring, and reduce everything to the case of a Noetherian ring. So that's the idea of the proof. So in the proof you do the following. Take non-zero element, so M, which is not equal to 0. This is an element in the given module M. Now, for shortness of the notation, set I to be the annihilator of this element M. So then we have a submodule, R modulo I, which is the same thing as the cyclic module Rm, which is a submodule inside M. So M is Noetherian, and any submodule of a Noetherian module is Noetherian. So the conclusion is that this quotient ring is necessarily Noetherian. So R modulo I is a Noetherian module, and of course this means that it's a Noetherian ring, because the ring is Noetherian if this is Noetherian as a module. Okay, so we have a Noetherian ring. So by the proposition we can say the following. So by proposition we get that there is an element, so there is prime ideal in this quotient ring, and I'm going to denote this prime ideal using the correspondence theorem P modulo I. So that's a prime ideal in this quotient ring. So there is such prime ideal such that this P modulo I is associated to the module R modulo I over the same ring. Right, so this Noetherian ring, in particular, can apply proposition when M coincides with the ring. So that would be a very special case, but I can use the special case here. So there is a P over I such that this is associated. Okay, and then I have the following claim. I claim that actually this prime ideal P, if I consider this in the ring R, this is annihilator over the ring R now of the element xm. Right. So if I can show that this is true, I'm done. I actually found a prime ideal which is associated with the given module M that annihilates element xm. So the only thing I need to show is this. Okay, so first of all, I can observe that P times X always contained in the ideal I. So how we can say this? Well, I is an annihilator of the element M, and wait a second. Yeah, so sorry, I forgot to introduce what x is. So I need to say that since this pi over I is associated, right, this is annihilator of one particular element. So I can say that the pi over I, so pi over I is annihilator of the element x plus I over R modulo I. Right, so this is how I introduce x, and pi is exactly annihilator of the xm, where this x is fixed by this condition. Well, then, if I consider px, well, px supposed to annihilate this in the quotient ring, but this means exactly this, that the representative of the class is a zero representative, so representative belongs to the ideal, so we have this. So this is follows from how we choose x. So this gives us one conclusion. So yeah, and of course, if px belongs to an ideal I, well, clearly px annihilates, well, since I by definition annihilates m, right? So it means that element p, any element in the prime ideal p belongs to this annihilator, right? So take product of px, the product belongs to I. If you multiply this on m, you'll get 0. So this gives us inclusion in one direction immediately. Now let's try to go in the other direction. So suppose we have yxm is equal to 0. So I'm assuming that element y belongs to the annihilator of the element xm. So I want to get an inclusion in the other direction. So if this is the case, then this product y and x has to be an ideal, has to be an element in the ideal I. So then yx is an I. But if you now again look at the definition of the element x, I claim that I can conclude that x actually, not x, y actually is an element in the P. Right, so everything that annihilates element x in this quotient ring has to be element in the P. So y is in the P. And this immediately gives us inclusion in the other direction. So now I start with any element y in the right-hand side, and it belongs to the left-hand side.
After we write proof, we extend that 0 plus m is lies in...
No, this is not plus. This is m not equal to 0.
Oh, it's not equal. Okay.
Yeah, so I need to take a non-zero element. So this m not equal to 0. Okay, so I have a little exercise which is not important for in general theory, but I think it's useful to know such an example. So if you consider a ring R, let's say, of continuous functions on the real line, so then the set of the associated primes of R over this ring R is empty. So of course the ring is not Noetherian. So our general proposition and corollary can be applied in this case. Okay, definition about two things. So again, I have a module. I take an element R in the ring, and I want to give a name for the multiplication map. So let's call mu sub R a map from the module to the module. This works for any module, and this just sends element M to the Rm. So just another notation for multiplication on the element and from the ring. So R is called M regular if the corresponding multiplication map is injective. So, and part 2, R is called the zero divisor on M. Well, if this is not regular, so if mu R is not injective, so it's quite natural definition. If this is zero divisor, it means that some product for some element M is actually equal to 0. So I want to use notation for the set of all zero divisors. So let me use notations such as Z of M. This is the set of all zero divisors on M. Okay, proposition, how this is all related to the associated primes. Well, if M is Noetherian, so if I'm at some point I forget to say that the modulo is Noetherian, in this section or in this chapter I always assume that all modules are Noetherian, because in this case we have these nice propositions. Otherwise we have such examples where theory of associated primes doesn't quite work. It can be an empty space. So for a Noetherian space, of a Noetherian module, we have the following: that the set of zero divisors on M is precisely the union of all associated primes. Well, we need to show two inclusions, and I claim that inclusion in one direction is a completely trivial inclusion. If I take the union over all associated primes, I'll get something in the zero divisors, and this is just by definition of associated prime, right? So any element, take an element in the union, it belongs to one of the prime ideals, and prime ideal is annihilator of some particular element. So that's a zero divisor for this element. So one inclusion is clear. Now let's go in the other direction. Let's take some R, which is a zero divisor on the module M. So there is a element M, so there is M in the M without 0, such that Rm is equal to 0. Okay, so but if I consider cyclic module Rm, since I assume that element M is not 0, I can claim that this module is not a zero module. Right? So I have a non-zero module Rm, cyclic module generated by the element M. Hence, I can say, by what we already proved, that there is an element P, prime ideal, which is associated over R with the cyclic module Rm. Right? Since the set of the associated primes is not empty. So I can say that this element P is actually annihilator of some element, say Bm. Okay, so this is the, so P is annihilator of the Bm, and what else I can say? Well, I can say that element R also lives here. Right, so R, we assume that R annihilates M. So for any element R, we actually constructed an associated prime. So this is prime ideal, and that's an annihilator of some particular element in the module M. So P is associated, and R belongs to this P. So for any zero divisor, there is a corresponding prime ideal. So this ends the proof. Okay. So whenever we do some construction in commutative algebra, we usually want to check two things. So this is about modules. We want to understand how this behaves with respect to the extension of modules. And then the second step would be to understand how this behaves with respect to the localizations. So next proposition tells us that if you have a short exact sequence, if 0, m prime, m double prime 0 is a short exact sequence, so then we have the following two inclusions. Associated primes of the submodule always form a subset in the associated primes of the module, and associated primes of the module belongs to the union of the associated primes of the submodule and the quotient module by this submodule. Okay. Proof again is not very hard. I claim that one inclusion is clear. So if you take prime ideal which is associated to the submodule, this is clearly associated to the module. Well, since you take this prime ideal as an annihilator of some element in the submodule, just consider this element inside the module. It still has the same annihilator. So one inclusion is, in this case, is quite clear. Okay, now the second inclusion. Let's do the following. If we take a prime ideal which is associated to the module M, so as we noticed in the very beginning, this means that there is a module N which is isomorphic to the quotient R modulo P sitting inside M. Right, so this is just a cyclic module. So P is an annihilator of some element M, and N is just a cyclic module generated by this element, of course, which is isomorphic to the R modulo P. Now let's set by definition that the L is the intersection of the two submodules, M prime and N. So in the end we have two submodules, L is the intersection. Now we have two cases. So the first case is that L is actually 0. Right, so this intersection of the M prime and N is a 0 submodule. Well, but then in this case, I can claim that N is actually submodule or isomorphic to a submodule in the quotient. Right? And if this is the case, I can say that P is associated to the M double prime.
Why is it so? They could have isomorphic means quotient model.
No, say by the correspondence theorem. Yeah. And the last implication, because, well, you have this submodule which is isomorphic R modulo P sitting inside M double prime, but this means that you have a cyclic submodule generated by the class of 1 plus P and with annihilator P. So in this case, this P is actually associated to the quotient module, and of course, as you can guess, in the other case, P will be associated to the submodule M prime. So if in the second case L is not a 0 submodule, then there is non-zero element X living in the L, and then annihilator of the X is exactly this prime ideal P. So this last thing follows from the exercise which I formulated in the beginning, that whenever we want to understand associated of this is precisely just one prime ideal P. So essentially what you need to show exactly what I have here. Whenever you take any class here and you try to understand the annihilator of this class, well, if this is non-zero class, then the annihilator is exactly P. Okay. So another proposition of this type. So if M is the direct sum of some modules, then associated primes of the M is the union of the associated primes of all these modules. Okay, so again, something is clear. So I claim that if you take the union of all associated primes, union of the associated primes of all such modules, and then this belongs to the associated primes of the module M. So this is clear. Right. This follows immediately from the definition, right? If you take something here in this union, that's a prime ideal that annihilates an element in Mi, but you just consider this element inside M, maybe all other components being 0, and that gives the inclusion. Okay, so one inclusion is clear, and in the other direction, well, we can do the following trick. So if P is associated to the module M, so what this means? Well, this is annihilator of some element in the module M, and since this is direct sum, this element M is a finite sum of elements in the Mi.
Can we construct short exact sequence 0, M1, M, other sum?
Essentially, that's what we're going to do. So the point of this proof is that this sum is not necessarily finite. So from this proposition, you immediately get this result when this sum is finite, right? Just by embedding, say, well, doing the standard induction that we've seen before, right? So you embed first component in the direct sum, the quotient as all the other components except the first component, then you do this by induction. But here, the sum is not necessarily finite, and that's the point. So this is why I need the argument that I'm trying to make right now. If this is annihilator of some element, this element is a finite sum. So it belongs to finitely many Mi's. So if P is associated with the M, I claim that I can say that P is actually associated to the, so another set J. So I take a sum of another set J of all Mi's such that I belongs to this set J, and this set J is finite. Right? So P annihilates some element. This element is a finite sum of components. So I just take all these elements, all the modules that contain non-zero components in this sum. So this is how I construct this finite sum Mi, where I is running over some finite set J. Okay, so since this is a finite set, I can immediately conclude by the proposition that we just proved that the set of the associated primes for this finite sum is a subset in the union of the same set J of the associated primes of Mi's. So this is by the proposition. by the proposition and by induction. So by these two things we can prove this inclusion. But the last step, right, what we want to show that so we want to show the other inclusion. We want to show that if I take the associated prime which is associated to M, it actually belongs to this infinite union. Well, well, first of all, we can immediately see that since this is just a finite union, this belongs to the infinite union. So this is in the infinite union. And oh yeah, so I think we've done here with this observation. So I start with the prime ideal P that belongs to this set, hence it belongs to this set, and by the proposition and induction we can say that this set is actually subset in this finite union, and this finite union is clearly a subset in this infinite union. So essentially we prove the proposition. We just need to find all the right steps in the proof. Okay. So that's an observation for direct sums. Of course, there is a natural question, is this true if we assume that the sum is not direct? So maybe I leave this as the next exercise. We'll show that in general, associated primes for the sum of two modules. So notice that the sum is not direct. So take a module M, take two submodules, take a non-direct sum. Then this is in general, it's not the same thing as the union of the associated primes of the M1 and the associated primes of the M2. So the question is, of course, to find the counterexample. You need to find the ring, or hint, try integers, or even over integers, this is not true, and then try to find a couple of modules. So R is Z, what are M1 and M2? Okay. So
Will be inclusion in one direction.
yeah, you get inclusion, but not equality in general. Yes. So proposition. No, inclusion you get just by that proposition. So now, next general observation is about the localizations. So let's fix a multiplicative subset. So S inside R is a multiplicative subset. And then I have two properties again. If I want to formulate this in an accurate way, I want to separate this into two statements. So first statement, if you take associated primes over the ring R and intersect this with the spec of the localization, well, of course the question is how I can think about this as a subset, as a two subsets of one set. Well, this is the correspondence theorem for the localization. So what are prime ideals in this localization? Well, these are precisely the prime ideals in the ring R, such that they don't intersect with the multiplicative set S. So I take this intersection inside the spec of R, and I claim that in general, without any assumptions, I can conclude that this is a subset of the associated primes over the localization. And part 2 tells us that
It should be S minus 1 M. Or S
Yeah.
minus 1 R.
And in part 2, we can assume that if prime ideal P is finitely generated, And the localization of this prime ideal, so S inverse P, belongs to the set of the associated primes over the localization of the module. So then this prime ideal P belongs to the associated primes of the module M over R. So of course I can say that in particular if R is Noetherian, right, so then this condition is automatic, then this inclusion we know from the first part without assumption that R is Noetherian, and this gives us inclusion in the other direction. So if R is Noetherian, we can have this nice formula that the set of the associated primes over R of the module M intersect with the spec of the localization is exactly the same thing as the associated primes over the localization of the module. So this is a nice formula that is true in a Noetherian case. Okay, so we start with the first part. So let's take a prime ideal P, which is belongs to the left-hand side. So this is associated to the M over R, and also in the spec of the localization. Okay, so the proof is quite easy. Well, since this is associated, I can say that R modulo P is embedded into M. So then what we do, we just localize this at S. So since the localization preserves the exactness, in particular it preserves the injective maps. So I'll get S inverse R modulo S inverse P is embedded into the S inverse M. So this is by the exactness of the localization. But that's exactly what I want, right? So the only problem possibly could be is that when this ideal is not proper. So in this case coincides with the S inverse R. But this can't happen because since we assume this condition, this is in the spec S inverse R, so it doesn't intersect S. So this we get because this belongs to the first thing, and this is not zero since this belongs to the second thing. So, and this is the end of the proof of the first part. So second part. For the second part I need to fix some notation. So let me say that P is generated by the F1 up to Fn. So notation for the generators of this prime ideal. Okay, so what we know that the localization is associated prime for the localization of the module. So it means that if I consider, say, some Fi over 1, and I apply this Fy, well, let me just say that the localization of the P is actually annihilator over the localization of the ring of some element that I'm going to call, say, X over S. So again, I'm just fixing notation. So this belongs to the, so this is associate prime of the localization of the ring. Well, this means this is annihilator of some element, and any element looks like such fraction. So then I can say that if I multiply Fi over 1 on the XS, then I'll get 0 for any I. Right? So this prime ideal, localization of the prime ideal is annihilator if and only if every generator acts as a multiplication of 0. Then there are elements Ti in the multiplicative set S such that Ti Fi x is equal to 0. This is again for any I. So I is running between 1 and n. And now I want to fix some notation. I want to say that the element T is just the product of all these T's that I constructed. So that's another element in the set S. So what I can say now? I can say that if I consider product Fi Tx, then this is 0, again, for any I between 1 and n. Right? So all such products are 0. If I multiply by other T's, it still will be 0. So any Fi annihilates element Tx. So it means that if any generator annihilates element Tx, then P, ideal P, annihilates element Tx. So we get such inclusion. So I want to conclude actually that P belongs to the associated primes of the M. So what I want to show now that actually not just in the sub-ideal, that these two ideals are actually the same. So let's try to do this. Let's take an element. So if I take an element, say G, which annihilates element Tx, well, what I can say then? I can say that if I consider fraction Gt over 1, then this fraction annihilates fraction x over s. So this is in the annihilator x over s. Okay, so then I claim that the product Gt is actually in the ideal P. Well, this fraction is what we called iota sub s. So this is an element of the iota sub s of the P, right? And now if I apply iota sub s inverse, I still get P. So Gt belongs to P. But what I can say also, I can notice that this T is an element in the S. So T is not in the prime ideal P. Because otherwise this computation doesn't make much sense, because the localization will be just the ring itself. And we want to assume that this is, of course, not equal to the localization of the ring. So this is prime ideal. T is not in the ideal P, so G is in the ideal P. And hence, P is the annihilator of the Tx. Okay. Next proposition, which will be useful later. So assume, as always, that M is Noetherian. So then any prime ideal in the support of M contains a prime, contains an associated prime. Well, the proof is quite easy. So what it means that P belongs to the support. It means that if I localize, I'll get a non-zero module. But I haven't actually said this explicitly, but localization of any Noetherian module is Noetherian, and localization of any Artinian module is Artinian, which is quite clear by the correspondence theorem for localizations. So this is a non-zero Noetherian module. Hence, the associated primes, the set of associated primes is not empty. So there is and we know how all prime ideals in the localization look like. So these are of the form QRP, so the extensions of prime ideals Q in the ring R. So we have a non-zero, well, we have non-empty set, we have a non-zero ideal like this, but this means by the proposition that we just proved that Q is actually associated with the M, and also Q sits inside P. Yeah, because if this is not the case, then this thing is exactly RP. So this is the unit ideal. Okay. Now we're actually going to prove something that I'm going to call theorem. So you can notice that not very many statements I call theorems. It's not because this is hard, because I think this is quite an important statement. So the statement is the following. If M is Noetherian, there is series of submodules. Well, first module is 0, which is I'm going to call M0. It is contained in some M1. The last module is Mn, and this coincides with the M, such that the quotients Mi modulo Mi minus 1 are all isomorphic to the quotients R modulo Pi. So where all such Pi's are prime ideals. Spec R. So this should remind you another statement. Remember when we discussed modules of finite length, we said that the modulus of finite length, if it has such filtration and all such subquotients, are simple modules. But simple modules are exactly modules of the form R modulo maximal ideal. So here we generalize from maximal ideals to prime ideals. And if you generalize this in this way, that all subquotients are quotients by prime ideals, this statement is now true for any Noetherian module. So this is another indication that in commutative algebra, if you know something for maximal ideals, maybe it's a good idea to understand how to generalize this to prime ideals. And the proof is actually relatively straightforward. You just construct this by induction, right? So you know that M is Noetherian. Well, you construct M1, which is isomorphic by R modulo P1. That sits inside M, right? So M is Noetherian. The set of the associate primes is not empty. So there is a submodule like this, R modulo P1. And then we just continue doing this by induction. So if quotient of the M modulo M1 is not 0 module, so if this is 0, we're done, right? So then our module is given as a R modulo P1, and if this is not 0, well, if this is not 0, this is again Noetherian module. So we just continue doing this. So I claim that we can take M2 now modulo M1, which will be isomorphic to the R modulo P2, and this is embedded into the M modulo M1. Okay.
Can it be non finite? This series.
No, this is finite because the modulo is not even, so this will be the end of the argument. So you continue doing this, you can continue constructing this more and more modules, right? So first you construct submodule M1, then you constructed module M2 containing M1, and so you start with 0, which is M0, then this is inside M1 that you constructed on the first step, this sits inside M2, and they're not equal actually, so this is an increasing sequence. Then you continue doing this, but this has to stabilize at some point since the module is not even. So since M is not even, the sequence stabilizes. Well, this means that on some step the quotient that we're constructing is actually a zero quotient. Hence, we get only a finite chain of submodules like this. So as you can notice that there are no, well, there's nothing in the statement about associated primes. So we only use associated primes to claim that there are embeddings like this. So if you don't know theory of associated primes, it can be quite hard to prove such theorem. Okay. And next important theorem. Again, M is Noetherian. Actually, we now associated 3 sets of primes to a Noetherian module M. We have the set of associated primes. We have all primes that we choose a chain like this, and any chain like this gives us a finite set of primes. So of course this set of primes is not canonical. You can take one module and you can construct 2 different chains such that, well, this set of prime ideals will be different. But what is actually still true is the following, that the set of associated primes of M is a subset of primes that we constructed in the previous theorem, and this is a subset in the support of M. So let me say that this set in the middle, so this set of primes for any prime filtration. So this chain of submodules sometimes is called filtration, and let's call this a prime filtration if all the subquotients are quotients by prime ideals. So this is just to give a name to the set of primes that we obtained in the previous theorem. So we have 2 such inclusions, and we have actually more interesting statement. So moreover, these sets have the same minimal elements. And also, one interesting observation that follows immediately, I don't want to write this, the set of associated primes is always a finite set for any Noetherian module. Of course, this is not true for a support. In general,
There's always a minimal element.
Hmm?
So there's always a minimal element for support.
well, minimal elements is just the prime ideals here, here, or here that don't contain any other prime ideals.
Yeah, I understand, but if associative is finite, we can find minimal element. But if it's not finite, like support,
We still can talk about minimal elements. This will be a prime ideal belonging to this subset that doesn't contain any other prime ideal from this subset.
yeah,
Well, what is true is that if you consider a set of submodules, then if the module is not Artinian, then there is no minimal element.
Yeah, that's what I want to say.
Here, I think you can always construct a minimal element if you just again apply Soren's lemma and take this infinite chain and then take the intersection of this infinite chain. Yes, it still makes sense to talk about minimal elements in all three sets. Of course, it's much nicer in the first two sets because it's just a finite sets, but for support it also makes sense. Okay. So we need to show two inclusions and then this moreover part. So proof. Inclusions are proved by induction on n. So where n is just how many prime ideals we have in the prime filtration. So the base of the induction so I think now we need to open window. Okay, so the base of the induction is quite simple. So if n is equal to 1, then the module you consider is just a quotient by a prime ideal. So in this case, we all know the answers for the associated primes. So for the associated primes, it's just one. Let's say this is P1. So this is just one prime ideal P1. Of course, the prime filtration, well, the second set is just again this set with one element P1, and the support is, well, definitely, what we can definitely say that the P1 is an element in the support in the support of M. Right? If I take this thing, localize this at P1, this is not 0. So we get these two inclusions in the case when n is equal to 1. These two sets actually coincide. This could be much larger, but at least P1 is an element in the support. Now, if I want to do the induction step, I consider short exact sequence where Mi is embedded into, Mi minus 1 is embedded into Mi with the quotient being R modulo Pi. Right, so we have such short exact sequence again, essentially by the definition of the prime filtration. And now we just apply everything that we know about the associated primes and the support. So we know that associated primes of the Mi are contained in the associated primes of the Mi minus 1 union with the associated primes of this quotient, but this is the same thing as the just Pi. And this immediately gives us this inclusion by induction. Now, for the support, we also have similar results. If you still remember the results, that support of the module in the middle is contained in the support of the submodule and the support of the quotient module. So support of the Mi I think it's actually equal. So I can say that the support of the module is the well, this is not the Artinian modules. It's definitely finite. Yeah. So using this, we can say that the support of Mi is the same as the support of Mi minus 1 union of the support of the quotient but again Pi is an element here. And this observation about the supports give us the second inclusion. So now we only need to show that moreover part is true. Okay. Suppose I take P, which is associated to the M, and this is minimal. Of course, I want to show that the set of associated primes and support has the same minimal elements, because if I know for these two sets, this will be true for the set in the middle. So let me take P, which is associated to the M and also minimal. So I want to, well, first of all, of course, I know that such P, I already know that such P belongs to the support. This follows from these two inclusions. I can again show this directly by localizing and seeing that this is not zero, but clearly this is in the support. So the question is why this stays minimal in the support. Okay, so if P is not minimal in the support of M, well, what it means? It means that I can find another element, say Q, another prime ideal, which is contained in the P, and Q belongs to the support of M, right? So this is what happens if P is not minimal. Well, but we proved a little proposition that any prime ideal in the support contains a subideal which is associated. Right? So that was a proposition that we proved immediately after we proved proposition about the localizations. So then there is some Q prime which is associated with the module M by that proposition, and Q prime sits inside Q, which also sits inside P. Well, that's a contradiction, because I assume that, well, now Q prime is associated, P is associated, and P can be minimal. So that is why I want to prove this proposition, because it is used here in the proof. Okay. So any element in the associated primes are still minimal in the support. Now let's go in the other direction. Suppose P in the support of M is minimal. Okay, so
Isn't it obvious that this minimal in associative set, since associative is subset of support?
yeah, in a way it's obvious, but well, I wanted to say, let's say a little bit, I want to be a little bit more precise. I wanted to say that MP is not a zero module, since this is in the support, right? So then the set of the associated primes is not empty, and then since I know that by the proposition about the localization that the set is the same as the intersection of the set of the associated primes with the spec of the RP. So this is contained in the support of M, and this is in the spec RP. And I claim that this is the same thing as the set consisting of only one element, PRP. So what we can actually, why we even need this argument? Well, the question is, you take prime ideal in the support, which is minimal. How do you conclude that this is actually belongs to the associated primes? The set of support is much larger set. So if this is minimal, then you can conclude that this is associated prime with this argument. Yeah. Well, since this is minimal. So we know the structure of all prime ideals here. These are prime ideals contained in this prime ideal, which is a maximal ideal. Right? If you have something else, then this is also, there is corresponding ideals. If you have something else, Q R P, then this Q is also in the support, and this Q is contained in the P. So this set has only one element. So from this we can conclude that that they actually P is associated to the M. And the last observation, as you said, is completely clear. If you know that this minimal element belongs to the associated primes, this stays minimal because it's just a subset. Okay. So I want to say something like terminology. I don't want to call this notation. So minimal primes of the support of M, or I can as well say V of the annihilator of M. This is the same thing, since I continue to assume that the modulo is Noetherian, at least this is finite. For finite we have this. So minimal primes correspond to the maximal irreducible components of the support. Right, so geometrically, of course, you're more interested in the maximal components. So algebraically, this corresponds to the minimal primes of the support. And this geometric intuition, okay, the why you reverse minimal and maximal in reverse inclusion, explains the next part of the terminology. So minimal associated primes are called isolated associated primes. Well, we know that irreducible subsets in this spec corresponds to the prime ideals.
Yes.
So, and under this correspondence, when you take an ideal and take V of this ideal, or in the other direction, you just take a closed subset, and this is V of some ideal. Under this correspondence, the inclusion can be reversed. So minimal elements in one set, this in the algebraic set of ideals, corresponds to the maximal ideals geometrically. The maximal elements, maximal irreducible. In this spec, yes.
Okay. Okay, thanks.
Yeah. So, and for this reason, this minimal associated primes are called isolated. And if there are other associated primes, well, these are called embedded. So non-minimal associated primes are called embedded. To make sense of this terminology, you need to think geometrically. So of course algebraically, minimal actually is something that is not, actually that is something that's embedded into something. But geometrically it's the other way around. So the terminology here is just geometric terminology. So we're going to see examples of this situation, and we have minimal and non-minimal associated primes from the seminars. But just to give you a brief example, and all the details will be postponed until we do the seminar. So in this example, you take polynomial ring into variables, and so this is R, and the module M is just the quotient of R by the ideal generated by the y squared and xy. And I claim that if you do the computation, that the associated primes is the set of two ideals, maximal ideal generated by the x and y, and prime ideal generated by the y. So try to prove this. And in this example, this ideal generated by y is isolated, and the maximal ideal corresponding to the point is an embedded point. So embedded. So you can try to draw, for example, a real picture of this situation. So you're going to see one irreducible component with this equation, and in this irreducible component you get one embedded point. So that's another geometrical reason why we're interested in this moreover part of the previous proposition. We're interested in the minimal elements because they correspond to the maximal irreducible components. Okay, now I also want to derive one corollary from this proposition. Actually, one corollary with three simple parts that does require any real proof. So first is, as I said, that if M is Noetherian, the set of the associated primes of M is finite. That part I already mentioned. The second part, again, let me just say, if M is Noetherian, first associated primes of M is a finite set. Then the second statement, well, if I want to understand the radical of the annihilator of M, I can take a finite intersection right? Since we already know that if you want to compute the radical of the annihilator, it's enough to take intersection over all prime ideals which are in the support of M. But when you take intersection, it's enough to take only intersection of the minimal elements. And the minimal elements are the same in these two sets. So any radical of any annihilator of Noetherian module is necessarily a finite intersection of prime ideals, general property of M being Noetherian. And 3, so if, again, M is Noetherian, then minimal primes over the annihilator of M are associated to M. So in particular, you can see at least some examples of the minimal primes by this third part. You compute this ideal, well, take minimal primes over this ideal, or geometrically, well, this gives you some closed subset in the spectrum. You need to find the maximal reducible components of this. Yeah, it can. Over means that there is inclusion in this direction. There is a standard terminology when they talk about subgroup and overgroup, subring and overring, subideal and overideal. It's kind of not used very often in the introductory courses, but there is such terminology. So this is ideals over another ideal. So do I need to prove this? Well, since I continue to assume that M is Noetherian, in particular, this is a finite module, then I can say that prime ideals over this thing is the same thing as the prime ideals in the support. So what I'm just talking about minimal ideals in the support again. So they are all associated, that we already know. So that's the proof of the last part of the statement. Okay. And still I want to finish with one more proposition. which I think is quite interesting. So assume that M is Noetherian, as before. Then the following are equivalent, 3 statements. So first, M is a modulo of finite length. Second, all associated primes are actually maximal, spec M of R. And condition 3, the support of M is a subset in the spec M. So length is finite, associated primes are maximal, all ideals at which this M is supported are also maximal ideals. Well, the proof is kind of straightforward when we know what we already know. So if the length is finite, this thing has a filtration, right, such that all the subquotients are simple modules, so it's R modulo maximal ideal. So this, by the proposition, by the theorem that we proved, associated primes belong to this subset, which we get from the maximal filtration. So 1 to 2 follows immediately from these 2 observations. Now 2 to 3. Well, this again follows from the theorem that I proved after I proved properties of the localization. If I take P in the support of the M, so then there is Q which is associated to the M such that Q sits inside P. Right? And
P is maximal,
yeah.
P is maximal.
Yeah, exactly. Since Q is maximal, we conclude that Q is actually coincide with the P. Okay, and finally 3 to 1. I assume that we have a module which is supported only on maximal ideals. So I want to show that the length is finite. We use the second inclusion from the second theorem that the set of prime ideals in the filtration is contained in the support. In the support, everything is maximal. So this set that we saw in the middle, P1 up to Pn, this is a finite subset of maximal ideals. So this immediately gives us 3 to 1. So we can characterize modules of finite length in terms of the support or in terms of the associated primes. And finally, corollary from this proposition, if you take a module of finite length, then support of the module is the same as the set of the associated primes. Well, you already have inclusion in one direction. Associated primes belong to the support. Well, take now any element in the support. That's a minimal element. Because we know that in the support we have only maximal ideals. If you have something inside, which is again maximal, so then they coincide. Okay, that's all I want to say for today.